Good afternoon, everyone. Thank you very much for coming. I have great pleasure to introduce good friend and great researcher from ANU. It's Yimao Wan. Yimao did his undergrad in Singapore, it's in NTU. It's a very nice university. And then he worked for industry for 6 years, part of that in Singapore, part of that here in Sydney. 2010, I think, he started his PhD at ANU with Kit McIntosh and did a great job on silicon nitride depositions, optimization, and a lot of also basic knowledge or fundamental knowledge about that. And today we'll summarize most of his PhD here in this presentation. So please welcome Yimao.
Okay, thanks, Steve, for introduction. And thanks, everyone, for your coming. So today, I will talk about my PhD work. And the topic is highly transparent and highly passivating silicon nitride for solar cells. So here is outline of the talk. We'll start with the motivation and follows with some fundamental reviews of silicon nitride properties. And then we'll come with some process development for the optimum silicon nitride, highly transparent and highly passivating nitride. And after that, I will present some recombination studies for silicon nitride passivated surface. And the silicon surface involved here are planar or textured. And the final part is to do some simulation to study the impact of silicon nitride properties on cell level and finish with the application of the nitride on IBC cells. So silicon nitride has been successfully implemented in silicon solar cells for more than 3 decades. And because of its fulfill 3 functions. The first one is comprise the anti-reflection coating, and it can provide the surface and the bulk passivation. And it also forms like a chemical barrier against the moisture or humidity or some sodium ions. So, and in this talk, I will focus on the anti-reflection coating and the surface passivation property. That means most of my study will focus on the optical property of silicon nitride and also the surface passivation property. So what's the challenge of silicon nitride? Research work on silicon solar cells. And here I summarize or review some data from literature by plotting the recombination versus the refractive index of silicon nitride. And the refractive index is taken at 632 nanometer. So, and the recombination results are taken from several studies, like from Loinga and Schmitz, Markel, and someone else. And they are deposited with different techniques, like remote PECVD or high-frequency direct PECVD, or some inline one or low-frequency one. So, but as we can see, all these results shows a classic change, which is the SRV, the surface recombination velocity decreases as refractive index increases, and thus irrespective of the deposition techniques. So that means the best surface passivation or the lowest surface recombination velocity is obtained by the silicon-rich nitride, which has high absorptions. And that means there has a trade-off between surface passivation and the optical transmission. And the focus and the purpose of this talk is or my PhD work, is to obtain an optimum silicon nitride which can provide very good surface passivation as well as provide a low light absorption. So this section will show some fundamental review of silicon nitride properties, and it will include the optical property, the chemical structure, or some electronic properties. The first one is the optics. So the optics refractive index are plotted as a function of the atomic nitrogen to silicon atomic ratio, and the atomic ratio present here was taken from the literature, and they were experimentally determined by either RBS or ERD. And again, there are several different deposition techniques here. As we can see, the refractive index shows a quite universal correlation to the atomic ratio. And this relationship can be calculated by the formula proposed by Bastard in 1988 using this formula. And it's in very good, fair agreement with the experimental data. So for my work, I didn't have any measurement or characterization on the atomic ratio. So most of all atomic ratio for my work is to calculate, use this formula from refractive index. And the second optical property is extinction coefficient or absorption coefficient, which is another very critical property for silicon nitride as an AR layer in solar cells. And the extinction coefficient K or absorption coefficient alpha is plotted as atomic ratio, and it shows a decrease generally with an increased atomic ratio, which means as the silicon nitride becomes nitrogen rich or more nitrogen atoms here, the absorption is low. And this trend is, if you go back to the refractive index, is actually the absorption coefficient generally decreases as the refractive index decrease. And the second property is chemical bond structures, which characterized by the Fourier transform infrared and has like silicon nitrogen bond density or hydrogen bond density or some like a bond peak wave number. And the first one is the silicon nitrogen bond density plot as function of atomic ratio. Again, and for several different deposition techniques. And as we can see, it's, again, the bond density shows a general correlation to the atomic ratio, which has a peak here at the ratio around 1.1. And if you calculate the refractive index from 1.1 based on the equation I presented just now, actually it's around 2.0 refractive index. And the next structure is hydrogen-related bonds with the silicon hydrogen or nitrogen hydrogen. Yeah, it has quite a big experimental error range. It can be calculated from, the error can be from the experimental measurement or from the calculation, like different proportional constant used in the calculation. But when we see the hydrogen or silicon hydrogen or nitrogen hydrogen, we can see also a general or universal correlation to the atomic ratio, which shows the silicon hydrogen decreases and the nitrogen hydrogen increases as the nitrogen to silicon atomic ratio increase. And this is within expectation as, like, say, there are more silicon hydrogen bonds as more silicon atoms there. And this behavior is consistent with the universal chain with silicon nitrogen we present just now. And another structure property is the silicon hydrogen peak wave numbers. And this is another good indicator of internal silicon nitride internal structure property, as the silicon hydrogen peak wave number will shift as different back bonding of like a nitrogen hydrogen back bonding to silicon hydrogen bonds. And we can see a universal increase in chance for silicon hydrogen peak wave number and the nitrogen silicon ratio. So that means as the more and more nitrogen atoms back bond to the silicon hydrogen bond, as shown in the right hand side, the wave number, the vibration peak wave number shifts higher. And the next property of silicon nitride is electronic property, which includes insulator charge density or interface defect density. And this is quite fundamental properties for surface recombination or surface passivation quality. And the first one is effective insulator charge. Again, it's plotted against the nitrogen to silicon ratio from a bunch of literature results. And it looks quite messy here, and that's the message from this figure, which means which means that the effective charge, or we can't observe a universal correlation between effective charge and to the nitrogen-silicon ratios. And some of my work is also included here. As we can see, for my work, the charge depends quite strongly on the deposition conditions. Like when I change the temperature, it doesn't change the film stoichiometry too significantly, but the charge can be varied in almost like a 1 order of magnitude. But when we change the pressure, we vary the stoichiometry in a quite wide range, but the charge in film stays quite, relatively constant. And the second property is the interface defect density. I can't find too much literature work for the DIT for silicon nitride, but there are still 4 here. And my results from the DIT measurement from my work is also included. It's quite similar to the charge, which a universal correlation between DIT and the atomic ratio can't be established. And this is not that surprised to see this one, because the interface defect density is an interfacial property. It presumably depends on the interfacial bulk property rather than silicon or interfacial structure property rather than the bulk structure property. Yeah, and let me do a simple conclusion or summary of the first review part. So we found, irrespective of the deposition conditions or techniques, the bulk structure or optical properties are universally correlated to the atomic ratio, but the electronic property, including charge or DIT, appear independent of the atomic ratio. And this is a significant finding. That means it promotes an opportunity to decouple the silicon nitride passivation property, which in principle depends on charge and the DIT, and as well as the capture cross sections. And we can decouple the passivation and optical transmission property, and therefore we can circumvent the trade-off between surface passivation and optical transmission we present quite a few slides ago. So the next section is process development, some experimental work to try to achieve or obtain an optimum silicon nitride which has high passivation as well as high transmission. Or following review, say we decouple these 2 properties. So methodology here is we varied several deposition conditions or parameters in R&R AK400 PECVD reactor, which UNSW has quite similar here. And the parameter varied here. We have precursor gas ratio and deposition pressure, temperature. There are another 2 parameters, like 2 plasma parameters, which I didn't present in this talk, as we found is the passivation quality is not that sensitive within our varied range. And then we monitor the passivation quality as well as the optical properties. So here's the results when we vary the ammonia to xylene gas ratio. So as the ammonia to xylene gas ratio increase, that means more ammonia is incorporated into plasma and into the film. The passivation quality decreases, and the refractive index decreases. And this is similar to the classic chains, which the highest passivation quality is obtained by some high refractive index film, which means silicon-rich films. And when we vary the pressure at 2 different temperatures present here, we can see, and again we plot the lifetime against pressure and the refractive index against pressure. And we can see the lifetime increases as pressure increases up to 0.2 millibar and seems quite saturated there. And this behavior we can see on 2 deposition temperatures, as well as to both P-type and N-type low-resist silicon wafers. So, well, the passivation quality improves as pressure increases, we see the refractive index decreases as pressure increase. So that means from this change, we can see it gives a good opportunity to get a very high passivation, like in this range, with very low refractive index film here, and which does the trade-off or the aim we want to target in this research. So when we plot the recombination, summarize the results of previous two slides, and then we can, by plotting the surface recombination against the refractive index, the blue line is the classic change I present at the beginning, which is the recombination decreases as an increase. And when I change the gas ratio, we get quite similar change. But when we change the pressure, we got an opposite change, which means the combination increases as the refractive index increase or as the film becomes silicon rich. And that's the area, or this region is the one we want to target, which has high passivation and also high absorption. High transmission force as an AR function, as AR layer. So let's look into more details about the passivation quality of the optimum film. So the lifetime is plotted against the excess carrier density or injection level on both p-type and n-type. And the two OJ limit models are plotted here as a reference. One is quite old one, like from Kerr and QS, and another one is quite recently, 2012, by Richter. So for p-type wafer, we can see over quite a broad range, the lifetime is above the Kerr limit, but it's well below the Richter limit. And for n-type, the lifetime measured from our work is well above the both limit, which means both OJ model or even the recent one proposed by Richter has some overestimation in intrinsic recombination in bulk. And we can also look at the injection dependence of this two type by silicon nitride, which has quite strong injection dependence for p-type, and is quite flat for n-type up to quite low level, 1E13 measured here. And there are several theories for the strong injection dependence for p-type surface passivated by silicon nitride. One is like a space charge region because of a positive charge in silicon nitride and cause some inversion layer on p-type surface, or some other theory like some hydrogen damage during the plasma deposition, or some recently theory proposed by Burst is some shunting of the edge of the inversion layer at the edge. So these are very, very good theories, but actually none of them has very direct experimental evidence. So it still needs some work to understand the injection dependence for the p-type surface by silicon nitride. And let's look more in detail on the optical transmission for the optimum nitride. I take several reference here, which has quite of state-of-art passivation from different groups and have different absorption coefficient. And I take one of the reference from Dutta from series, which shows the lowest SRV on p-type surface, but is passivated by the silicon-rich nitride. And from the optical simulation by OPER, we can show some advantage of the low absorption or high transmission from our film. So for our film, we have a refractive index close to 1.9, which is close to stoichiometry, and the recombination is 1.6 centimeter per second on p-type wafer. So the simulation is done on the random texture pyramids with a silicon thickness of 180 micrometers. And we have done the simulation on cell and the simulation under the EVA or glass encapsulated. So we can see our optimum silicon nitride or low absorption silicon nitride shows like an enhancement of current generation by around 0.66 milliampere per centimeter square for the encapsulated cell, or is even higher for the cell operating on the air. And this the enhancement is basically due to the lower absorption current for both cells. And then another property of this optimum silicon nitride is the thermal stability. So there are a bunch of films and with different bond density, but all of them shows quite good passivation for the as-deposit film. That means after the deposition from PECVD chamber, and then submit to the RTA rapid thermal annealing reactor at 800 degrees for 5 seconds. As we can see, all the films actually degrade a lot after firing, which means the optimum silicon nitride developed in this work has very poor thermal stability, and is quite correlated to the silicon nitrogen bond density, which means the higher bond density has less degradation or has higher thermal stability. Yeah, so they still require some further works to improve the thermal stability of this highly transparent and highly passivating silicon nitride. But not all cells requires the firing stability. Like recent very popular one, like the electroplated cells, which don't require very high temperature. So this silicon nitride still has some quite significant application, particularly on the high efficiency laboratory scale cells. So the second conclusion from my work is based on optimization and process characterization. We obtain a single silicon nitride, which can provide both high passivation of silicon surface as well as high transmission at short wavelengths. So next section I will present is to do some fundamental recombination studies for silicon nitride passivated surface. And this is done on planar surface as well as a texture surface. So the first one is on planar surface. So the methodology here is we extract the recombination, surface recombination as a function of the injection level from the measured effective lifetime. And then we probe in the electronic properties like DIT or charge using the capacitance voltage measurement. And based on the defects or the electronic properties, we can model the recombination we obtained. So the first one is the extraction of a recombination based on this formula. So it's extracted from the effective lifetime and after counting the bulk contribution and the thickness contribution. And we also compare to the state-of-art literature results. And most of them focus on the very low resistivity p-type wafers, like 0.7 up to 1.5 ohm cm substrate. And we can see all of the passivation or recombination results, they have quite similar injection level or injection level dependence, which is for the p-type surface, which might indicate they have quite similar, interfacial or some electronic properties. And for our case, we obtained the lowest recombination after OJ correction, and it's 1.6 centimeter per second on p-type wafer. And then we probe the electronic properties using CV. So the DIT and the charge can be extracted from the high frequency and the quasi-static CV curves. And the DIT for our optimum film is 3E11, and the charge is around 5.6E11. And in order to investigate to model in the recombination based on the defects, we also need the capture section. Unfortunately, I didn't have any measurement based on my own study, and I take some capture section results from literature, which presented by Jan Smith in 1997. So what he got is there are 3 defects in silicon nitride: defect A, and B, and C. And these 3 unique defects has quite unique number of capture sections for hole and the electrons. So I take these 3 defects and combine the DID and the charge measured from CV measurement. Then we can model the recombination for different defects type. And here's the results. So the dashed line is a modeled or calculated recombination based on 3 different defects we just present. And we compare to our extracted recombination. Then we can investigate which defects is the dominating recombination active center at our silicon nitride and silicon interface. So in this model, we adapted the latest silicon OJ limit or intrinsic bulk model by Richter, and we assume single defects at a single energy level, and also assume the capture section saturates from this measurement. So because for this measurement, the capture section seems not saturate, it might keep increasing or saturate some level. But in this case, we just take the highest value from here and do the modeling. So from the comparison results, we can see either defect A or B is likely to dominate the recombination at the interface, but definitely not defect C. We don't, make strong conclusion like say is defect A the domination is just because the modeling error range, the error of the modeling is quite high because of the very high error for the capture sections. It can be the order of magnitude error range. But defect C is quite far away from there, and from Schmidt's study, they conclude the defect C is caused by the ion bombardment to the silicon surface during their low frequency PECVD reactor. And definitely for this PECVD reactor, which has a high frequency microwave plasma or radio frequency plasma, and the ion bombardment to the surface is unlikely to happen. So the third conclusion from the study is we obtain a low recombination on p-type surface, and the charge it has 3E11, and DID has 3E11 and has 5.6E11 charge. And from modeling, we can conclude that defect A or B presented by Schmidt is likely to dominate recombination at the interface. And next study is a recombination at texturing. And the methodology here is we employ the optimum deposition condition, which is for the optimum silicon nitride, but we still vary the precursor gas ratio, because that is still the most sensitive parameter to obtain a wide range of refractive index, which means a wide range of film stoichiometry. And then we monitor the recombination as a function of a refractive index on 3 types of surface or morphologies. So we have planar 100, planar 111, and the texture with random upright pyramids. So by comparing the recombination to like a planar 111 to 100, or the texture to planar 111, then we can examine the relative contribution of its orientation factor or the texture pyramids factor to the total recombination at the texture surface. And then we probe the electronic properties by the depositing the corona charge. So that means we apply corona charge on lifetime sample and then measure lifetime again, or monitor the change of recombination. And the reason for this one is for the conventional CV measurement is almost impossible to do the contactable CV measurement on the texture surface because of the very high leakage current. But we can still access some, qualitatively access the electronic properties by corona charge. So for the recombination at the texture surface, there are 3 drivers usually proposed for the enhancement of recombination at texture. The first one is enlarge the surface area, like by converting planar to texture or pyramids. We have close ideal case like 1.73 times higher, a factor of 1.73. And the second factor is 111 oriented surface at texture surface. And we denote this factor as FO, as comparing a recombination of 111 to 100. And the third factor or contribution is the presence of the concave or convex of the texture features. Like in this case, the pyramids, we have vertices or edges associated with the pyramids. And we denote this factor as FV by comparing the recombination at the texture to the recombination at the planar 111. And here is the recombination results. And this result is after surface area correction, which means like for planar, the area ratio is 1, but for texture surface, we use the area ratio like 1.7. And firstly, is a planar 100, which the recombination shows quite similar trends to the classic trends, which this is like a representation of from Laoinga, shows a recombination decrease as film becomes silicon rich. And this is quite consistent from our experimental bivariant gas ratio. And then is a planar 111 and the texture surface. But please remember that recombination present here for texture surface is after correction of a factor of 1.7. Yeah. So as we can see, firstly we can see for all the three types of surface morphology, planar, 100, 111, or random texture, we obtain a low and a relative constant recombination over a wide range of refractive index. And that means we open a wider, even wider optical window or process margin to optimize the optical properties or for AR function, and without any like sacrificing the passivation quality by silicon nitride. And the next result is we study the ratio by comparing the recombination ratio, comparing the different methodologies. Then we can study the relative contribution from different factors. The first one is the orientation factor. So when we compare the SRV or recombination at planar 111 to planar 100, then we can see the FO is relatively constant and low across the whole refractive index study here. Is from very nitrogen rich up to amorphous silicon. And that means and we can comment later. And then we present the recombination ratio for pyramids or vertices or edges by comparing random texture to planar 111. Then we can see the ratio relates strongly to the refractive index or to the film stoichiometry of the film. So it shows quite high ratio and decrease strongly up to like 2.3. So for the film above 2.3, the recombination ratio is quite close to the unity 1.0. So the result means the orientation factor FO is constant low, which means the recombination at the texture surface when passivated by silicon nitride has less orientation dependence. All the orientation 111 orientation doesn't contribute quite high additional recombination. But when we look at FV, which relates to the pyramids, vertices or edges, it is quite high at the lower end, which means when passivated by nitrogen-rich nitride, the relative contribution from pyramids is high, or the other way, in other words, means the recombination of texture when passivated by low refractive index nitride is very sensitive to morphology. But when passivated by silicon-rich film, there's the increase at texture is negligible. And Then the next study I want to present is to probe in the electronic properties on texture surface. This is a big challenge because of high leakage, but we still can use some corona charge and monitor the lifetime. So here are some example of the recombination as a function of the applied charge. So for silicon nitride, there are 3 types of behavior for recombination versus charge. The first one is the red color when passivated by low refractive index film. So it shows a quite classic or typical change of recombination to charge. So as apply the positive charge to make the film accumulation, the recombination decrease. And as application of some negative charge, the film will become depletion, and the highest recombination happens at some level which the carrier concentration of electron and the hole are approximately equivalent, and that's also the cancellation or balance of the applied charge to the insulated charge. So which means we have some negative charge here to cancel out the positive charge in silicon nitride film. And in this case, we can qualitatively access the recombination due to defects. So we denote SiT, and as well as the charge in silicon nitride film, that means the negative effective charge. And the second case of nitride is when I apply charge, it shows quite similar, which it denotes as by blue color here. It shows quite typical for the behavior for the accumulation region here. But when we apply the negative charge, it never comes down, the recombination never comes down. And we suspect this is due to the injection of negative charge into silicon nitride film and cancel out the positive charge, in film. So that means when you apply, as you keep applying the negative charge on silicon nitride, and that means keep injection negative charge into the film. So the film is always stays almost like some balanced states, and the combination for the silicon nitride passivation doesn't change. So in this case, we denote the first recombination value as the SiT, which is equivalent to the interface defects. And the third behavior is for the silicon-rich nitride, has refractive index of 2.5. And for this film, no matter how you apply positive or negative charge, you can't see any significant change in the combination. And when you monitor the voltage or the charge amount on surface, you measure, basically you can't measure any charge on surface or voltage potential change on the surface. So we suspect this behavior is due to the leakage of the film is too high, and the application of corona charge on top can't sustain or can't stay on surface for quite a significant time, at least for the measurement of the lifetime. Okay, sorry. So by extracting the SiT from this measurement and also the charge, then we can study the relative contribution of either DIT or charge, the contribution to the recombination at the texture surface. So here is the results. By plotting the SiT as a function of S0. S0 means the initial recombination without any corona charge. And also by plotting the charge as a function of S0 or S0. And again, all this present value here is after surface area correction. So firstly, we can see the recombination for 3 surfaces like 100, 111, or Rentex. It shows quite not quite linear correlation between SiT and S0, which means the recombination at all the 3 surfaces is contribute or is dominated by the interface defects. But we can't but we can't establish quite strong correlation between charge and the recombination. So the result means the recombination at texture surface or the planar 10111 is primarily determined by the interface defects rather than the charge in the film. So the first conclusion from this study is we obtain a constant and low recombination on both planar and the texture surface, and thus over a wide range of n. That means quite wide or precise window for optics. And for the recombination, when we passivate by the nitrogen-rich nitride, the increase in recombination at texture is high, and the high recombination is due to the presence of the vertices or edges associated with pyramids, rather than due to the orientation, 111 orientation. And it is the coronal charge lifetime measurement reveals it is primarily caused by the high DIT rather than a reduction in charge in silicon nitride films. And when passivate by silicon-rich nitride or even amorphous silicon, the increase in the combination at texture surface is negligible. So the last part of the talk is to present the impact of silicon nitride on cells by simulation, and also one application onto N-type IBC cells. So in this simulation, silicon nitride functions as a front surface passivation, as well as an anti-refraction coating layer. And two types of cell structures are started here. One is P-type PERC. So nitride is to passivate a textured N-type phosphorus diffusion. And another structure is an N-type IBC, which the front surface has no diffusion. The simulation is performed using Quokka, and the optical is simulation using OPER2, using some parameters here. And the cell is operating in air. So the optical simulation is to use the refractive index and the extinction coefficient measured from previous experiments. So first one simulation result is ARC performance. So the simulation is to optimize the silicon nitride thickness to maximize the generation current. So as we can see, as the refractive index increases, the optimal silicon nitride thickness decreases, and the refraction increase, and the absorption is almost negligible up to the refractive index 2.0, and increase quite significantly. And the final or ultimate generation current shows quite constant up to 2.0 and decrease significantly, partially due to the high diffraction as well as high recombination. And the cell results on P-type PERC cells. So we use an experimental determine the recombination value and also experimentally determine the optical properties. Then we can simulate the cell parameters here. So it shows both VOC and fill factor increases up to around 2.1 refractive index, and then shows quite constant, but the short circuit current decreased significantly, and the overall efficiency is increased peak some value at 1.9 nitride, and then decreased significantly, from the recombination and also the optics, we can see that the low efficiency for the refractive index less than 1.9 is due to the high recombination, and for the low efficiency for very silicon-rich film is due to the high absorption. And here is IBC cell results, and it shows quite similar trends to PERC cells for the VOC and the fill factor. So it increased quite significantly and then stay flat. But the current the color behaves quite different to the PERC cell. Is basically due to the IBC cells are very sensitive to the color of IBC sensitive to the recombination at front surface. And the final efficiency is shows some optimum for refractive index 1.9 here. And again, the low efficiency for low refractive index film is due to the high recombination. And for the other part, for the silicon-rich film is due to the high absorptions. So the final is the application of this optimum silicon nitride on IBC cells. So the nitride is applied on IBC front side, and the front is textured and no diffusion. And for the details of cells, we have several publications on the design and the fabrication and the characterization of this cell. You can find in some other publications. And here is and the result is we achieve a 24.4 high efficiency on IBC cells. And the final conclusion of this part is the simulation shows the optimum silicon nitride for both cell structure has an refractive index at 1.9, and that's because of high surface recombination for low refractive index film and high film absorption for silicon-rich films. And the application of the nitride enables on IBC enables a 24.4 high efficiency. Okay, here's a final summary of the talk. So some key points here is firstly, we can't see any universal correlations between the surface recombination and the bulk structural optical properties. And that's a good chance to decouple the two properties, the two silicon nitride properties. And we obtain a highly transparent and highly passivating silicon nitride film, and the application on cells enables a 24.4 efficiency. And the recombination studies on texture surface shows the increase in recombination of texture is related to the presence of vertices or edges associated with pyramids rather than the 1-1-1 orientations. And it is primarily attributable to an increase in defects rather than a decrease in film charge. Thanks.
So we have time for a few questions. Yeah, that's okay.
Hi, thank you for the presentation. A couple of questions. You start with a review of effects silicon to nitrogen or nitrogen to silicon ratio on a range of properties. Can you comment on the effects of hydrogen content? Are there any general effects of hydrogen content on the same properties?
You mean the hydrogen?
Just total hydrogen content in nitride, which can be varied from 0 to up to 15% atomic.
Yeah. I don't have a review on the hydrogen impact of hydrogen on the atomic ratio, but we do see some correlations between like if you see this graph, yeah, it shows quite a big range of error bar here. But when you study the ratio of silicon hydrogen, or the other way, or nitrogen-hydrogen bond density, the ratio of nitrogen-hydrogen bond density to silicon-hydrogen bond density, it correlates quite well with atomic ratio. So that means, yeah, it shows quite linear correlation actually.
So is it good to have more hydrogen or less hydrogen?
It doesn't mean relatively higher content of hydrogen. It shows some relative contribution of hydrogen-related bonds. Yeah, you're right. The nitrogen silicon atomic ratio determined experimentally by RBS or ERD actually, yeah, doesn't reflect. I don't reckon it reflects some information of hydrogen contents here. Yeah.
Just another question. In your experiments on nitride passivated wafers, did you anneal the samples after nitride deposition? Or is it nitride deposition was the highest temperature experienced by your wafers? for which you determined all range of parameters, your surface recombination velocity in particular and lifetime.
Yeah, that's the one. Is all this passivation quality obtained in this work is by the as deposit film, which means no annealing or other treatment has been done, and it shows very good passivation. And as I present in the thermal stability slides, this film actually has very poor thermal stability. So when you anneal or fire this film, the passivation degrades quite significantly.
Because real cells are expected to be fired after the contact.
Yeah, that's the one. Yeah, that's true. So this cell is very hard to apply this cell to like conventional cells for some metal firing process. Yeah, but it still can be applied like some low temperature process like ANU developed IBC has the thermal budget is very low. I think, and recently the popular one is electroplated cells, which has quite low thermal budget.
Okay.
Yeah, thanks.
More questions?
Hi, thank you for your talk. So I saw a model that you model the surface recombination velocity by considering the DRT, the capture cross section, and effective store charge density. And I'm wondering how do you incorporate the store charge into your model?
Okay. Yeah, if you use the model proposed by Grish in 1988, you still can add in the contribution of charge into the formula. I don't have the details of the spreadsheet here, but it is possible to incorporate charge into the model with some spreadsheet. Yeah.
So the charge will impact the NS and PS, the concentration of the excess carriers near the surface. And this one goes to the Schottky-Reed Hall equation.
Yeah.
So the Jewish one will help you to calculate what is the concentration in the surface, that it's different from the concentration in the body.
Thank you.
More questions?
For the graphs that shows the peak efficiency, where efficiency increase and decrease.
Yeah.
Yeah. I mean, is this recommend or advise the optimal thickness of the nitride silicon layer, or what's it indicate? This is maximum peak efficiency.
Yeah. This simulation shows figure out the optimum refractive index of the silicon nitride film rather than thickness. The thickness is a quite, free variable to adjust, or you can adjust to optimize the generation current. So yeah, for different refractive index shows here, they have have different optimum nitride thickness, which shows in previous slides. The optimum silicon nitride thickness depends on the refractive index. Yeah.
I have some more questions.
Yeah.
So it's great work, but do you think that some of the conclusion is really related to the system? For example, that you use the AK400. We know that what and how the Maya tools, for example, some of the range will be thermal stable. So it means that it will be a bit different. So can it be that some of the conclusion for exactly about the ratio will be related more to the system and less to the silicon nitride? Or it will be related to the silicon nitride that's produced by very specific system?
Yeah, that's a very good question. Actually, is from the review I present, is like if you study the bulk property like the chemical bond density of structures or the optical refractive index, the property actually is quite independent of the deposition techniques or conditions. So it shows quite a very good correlation of this bulk property to atomic ratio. But yeah, right, you're right, for the recombination property or passivation property, it seems depends quite strongly on the system or reactor configuration used to deposit silicon nitride. And the fact is, it's really a bit hard to replicate this highly transparent and highly passivating nitride on other PECVD reactors. So because of different plasma chemistry or different the chamber geometry, or yeah. So the conclusion or suggestion for this one is for the bulk property, I don't think it depends quite strongly on, I mean, the relationship between bulk and atomic doesn't depend on the system. But for the passivation, it depends quite strongly on the PECVD reactors.
Okay. And just small, so the conclusion about the textile compared to the planar. So it's very different when I speak about the impact of the orientation. That's very different from thermal oxide, for example. So is the reason is because there is hydrogen in the film? Because I think that aluminum oxide behave the same, so it's independent of the orientation. So what is your opinion?
Yeah, that's a good observation. Yeah, so for thermal oxide, it usually shows like 5 times higher recombination on 111 orientation than 100 orientation, but not for silicon nitride. And even for silicon nitride, it depends on the film stoichiometry. So for nitrogen-rich film, it shows high recombination on texture, but for silicon-rich or amorphous silicon, it shows less dependence. One of the theory or hypothesis I have here is due to the growth methods is different. Yeah, hydrogenation maybe is one of the factor as you like hydrogenate or forming gas annual thermal oxide. The orientation factor will be reduced a little bit, but it still can't be reduced to unity or 1. And one of the theory we have is is due to the growth for the deposition, which has, so that the film is deposited on top of the surface rather than growth reaction with bulk silicon and expose the orientation in the bulk. So compare the thermal growth and the deposition process, the exposure of 111 or 100 or the dangling bonds is quite different. Yeah, but I didn't see any of the literature on this research. That's a good research topic. Yeah.
More? So let's thank Yimao again.
Thanks.